All right, good afternoon. Welcome everyone to Security 300. This talk is going to be about how Google's infrastructure helps enable us to quickly respond to incidents, like things like Meltdown and Spectre. I'm Brandon Baker. I'm tech lead for cloud security at Google. I'm responsible for the security of our cloud infrastructure and of the security of the services that we run on top of cloud. I'll be co-presenting today with Andy Chang.
Hi everyone, I'm Andy Chang, one of the product managers on Google's security team. And so we're very excited to be able to share with you how Google's security architecture and infrastructure, including the technology, the people and process, allow us to address at scale incidents of this type. Whether they're at the scale and severity of something like Spectre and Meltdown, which were fundamental flaws that were found in most microprocessors today, and which impacted the entire industry, or whether, in another example, they're a targeted attack on a specific Google service. In both cases, the infrastructure security design that we have has enabled us to respond to these and mitigate these without any impact to customers and without any effort from customers. So today, what we'll cover is really set up in 5 stages. I'll talk about the overview of Google's security approach. I'll also talk and highlight some of the key technologies, and then turn it over to Brandon to go deep on both Spectre and Meltdown. And we'll take a trip in the Wayback Machine, back to 2014, and talk about an App Engine breakout attempt. We'll then close with a summary of really the different things that are in play across technology, process, and people, which again enable us to respond to these things without impacting customers and without any effort from customers. So first, to emphasize that in both of these incidents, these were mitigated by Google and Google teams without actually any impact on customers, their data, or on Google or Google's data. And so no data was harmed in the creation of these events. So at Google, we really think about security in 5 pillars. And we focus product design, technology, people, and process around these 5 pillars. The first of these is really around platform trust, the core technologies and that we create to drive security, protection, monitoring, identification within the platform. And this will be the focus of most of the technology piece of this talk. In addition, we have technology and products focused around the full life cycle of data, not just in data protection. So collection, discovery, consent, access, protection, wipeout, takeout, that full life cycle. In addition, we also have technology focused around policy and control and identity and access management to allow us first to specify what we think is the proper behavior and then to detect and enforce on those behaviors, as well as for us to have your identity be a key thing that defines what you have access to and what you authorize on. In addition, we have a 4th pillar focused around application security. So that's really around the different pieces that allow both the applications we build as well as the applications you build on our platform to stay secure, again, from both a visibility, controllability, protection, detection standpoint. And then lastly, the 5th pillar that we focus and build process, technology, and people skills around is around our operations and risk management. How do we actually operate the platform, and how do we operate the infrastructure that you guys develop on for success and for security? The bulk of this talk will be focused on really 3 of these. The platform trust pieces and the underlying technologies form the majority of how we address both the Spectre and Meltdown incidents, as well as the attempted App Engine breakout, in addition to application security, and then the people and process and operations. For those of you who've attended previous Google Talks at Next or other talks around our infrastructure, this diagram is probably fairly familiar with you. We think about the security stack at Google really in 9 layers. And the core philosophy at Google has always been defense in depth at scale by default. In other talks, previously, we've gone through each of these 9 layers. And the thing to take home today from this is that both horizontally within a layer, we have multiple layers of protection so that there's no single point of failure. And then across each stack layer, as you go up and down the stack, we have multiple layers, again, that prevent you from having one single point of failure. For this talk, we're going to focus on really 3 areas. First, around our hardened hypervisor and the curated OS images. In addition, we're going to talk about live migration as one of the key ways we did at-scale patching. And then finally, we're going to talk about how both from a process and technology standpoint, our teams do incident response, forensics, as well as the sandboxing technology that protects a lot of our applications. For the balance of this talk, we'll be, again, as I said, focused on technology, process, and people. So those color codes, you'll see those in the upper left hand of each slide as when it's relevant, so to focus in on that. And that'll be true for all three of the main topics we're covering. As a preview of some of the things Brandon's going into much more detail about, we will be talking about our purpose-built hypervisor, operating system, and the application pieces around really the containerization that's core to a lot of how we deliver services, as I think Diane talked about in the keynote, and really the consistency and homogeneity of our underlying infrastructure, which enables the next two items, right? The ability for us to do live migration, the ability for us to do continuous patching. We'll also be talking about sandboxing technology in general that we apply to provide multiple boundaries of security for applications, as well as our gvisor sandbox, which we open sourced back in May. You know, as I think Diane highlighted in the keynote, Google loves containers. We run a lot of things within containers, including our VMs, including everything in GCP. Containers really give us that abstraction boundary and, importantly, an isolation boundary for resources, for execution, also for us to kind of manage quality of service on CPUs. To give you a sense of context around this, when you run a service on GCP, you're really running a service within a container that's running on a guest OS that's within another container that runs on our host OS. As I think we highlighted in the morning again, on a weekly basis, we start over 4 billion containers. So with that, I'm going to transition over to Brandon, who's going to talk to you a lot more in depth about both the two incidents that we're talking about today.
Thank you, Andy. So how many of you here remember hearing about Spectre and Meltdown back in January, right? It's a pretty fundamental discovery. And what made it so interesting, so unique, was that side channels as a vulnerability class have been known for a while. Right? There was research in the early 2000s that said, look, if you have a crypto algorithm and it accesses memory in a certain pattern based on bits being in a key, you could use that to derive information about that program's behavior. What was different with Spectre and Meltdown was a realization that the modern CPUs, most modern CPUs, are constantly running a speculative engine, another set of programs, basically, that you don't have control over, which are racing ahead and trying to fetch memory that might be useful to the real program when it gets to around later. And it'll do things like try to speculate and estimate which branches might get taken, and what an interesting memory then is useful to try to pull in. And it's this speculative behavior that turns out actually leaks a lot of information, a lot more than anyone really realized. So much so, actually, that you can read out the entire contents of memory from an unprivileged domain, whether it be a user space process or a virtual machine. And what this had is the potential for an impact to affect how VMs could be isolated from each other, or how a process could be isolated from its operating system, or how a JavaScript applet could be isolated from the browser that it's run in. So with this discovery in mind, I want to take you through a little bit of sort of an inside look of what this looked like at Google in responding to this, with a focus around cloud, but also a realization that this affected and impacted the entire industry. So we'll start kind of the Wayback Machine here back to June last summer, when Project Zero discovered this issue. There was a period of time, then we transitioned from July timeframe, where with this as a discovery and a realization, how are we going to fix this? How could we actually respond to this, right? This is a fairly fundamental flaw in modern CPUs that we all depend on. We needed to respond, though, because the potential impact to the industry was too great. But we also had to develop mitigations and workarounds in such a way that didn't really impact performance. Right? That was a very important element to all the consideration I think you were doing in this time frame. Did the fix have to come from microcode? Did it have to come from hardware? Did it have to come from software? Were there things we could do in the compiler? This is sort of this time frame where a lot of experts from a wide variety of disciplines and fields came together and spent the time to think through this. And I'll talk a little bit more about sort of what those mitigations were and why they were effective and how we got those out into production, right? Because deployment obviously is a very serious consideration, right? This was a set of flaws that we had to basically patch every machine at Google to address. And then it sort of moves forward to this last period of time frame for disclosure, right? Coordinated, responsible disclosure, super important given the wide impact of this affecting the entire industry. And I have to say, as we were going through this time frame, every day, every week, was always this concern around, was this going to be leaked? Was somebody going to also co-discover this? There was a security researcher in July who made a really, really close discovery of something very similar to this set of problems, but couldn't quite get the implementation details working and quite right. And so, there was a brief kind of, okay, can pause and get back into this. Because it was important that we also made sure that not just Google, but the whole industry was ready to go when it was time to announce this issue. And as part of that, thinking through this timeline of, okay, where is the world, where are people thinking about side channel attacks, speculative execution, how much interest is there going on? Is there awareness of this issue? Kind of thinking through this trend. And amazingly, we were actually able to sort of keep this as a coordinated disclosure. And really, it wasn't until January 3rd when this actually came to light, mostly to plan. So when I talk about some of the details, kind of a refresher or maybe sort of a deeper dive into how this thing actually works and what the variants were. There are many variants of this class because in some sense this is a new class of vulnerabilities. And at the time, sort of the June discoveries of last year, the ones we were dealing with, responding to, these were the 3 variants that we were looking at. And I want to call these out too because each one required a different mitigation and a different part of our stack. So the first variant here is something we call bounds checks bypass. I mentioned there's that speculative engine that's always sort of racing ahead. It skips a lot of important checks, things that normal software, when it actually really does finally execute, will do. For example, check within the bounds arrays or within limits or greater than, less than checks. Those are checks that the speculative engine simply doesn't bother with because it's just trying to race ahead and be useful to fetch as much memory in as it can ahead of time. Well, it turns out that that's actually a pretty useful thing then to then find interesting code gadgets where you can induce the speculative engine to race ahead, read and touch a bunch of memory, and then affect the subsequent behavior of the speculative engine. And it's that chaining of those events that actually leaks information. The second variant, branch target injection. This is also another behavior that the speculative engine does. When it encounters a branch, it has to decide, okay, what's most likely to happen here? Am I most likely to expect the branch would be taken or not taken? Right? And it turns out you actually can either find or introduce or inject interesting branch target, again, sort of gadgets, into the address space of the thing you want to try to leak information out, say it's the kernel or a hypervisor, and use those to sort of, again, watch and steer that behavior, watch the pattern of memory that's accessed, and then from your own domain, time how your memory accesses work, and that actually, again, ends up leaking bits of information at a time. Repeat that a few million billion times, and you've read out the memory of the machine. And the last category, Meltdown, given a slightly different name, given that its behavior is a little bit different, right? I mentioned these other ones are more sort of the speculative behavior and branching and sort of touching memory. Meltdown was different in that it's basically just a fundamental privilege check that the speculative pipeline doesn't bother to do until it's all done with speculation, right? And this is the user kernel supervisor page table bit. And what this means is actually the speculative engine, when you're in a user mode process, will happily go and read right on through into kernel memory in the same address space. Something that's normally prohibited and would generate a page fault. The speculative engine doesn't check that bit until the very, very end of speculation, again, on some processors. And again, what that means is you can effectively then induce the speculative engine to read memory that your program should never normally be able to read, time access patterns, leak information out. Okay. So with the ideas here of these issues, I'm going to take a step back for a moment and talk a little bit about our infrastructure stack and some of the security philosophy that we have at Google. One of our fundamental guiding principles really here at Google is a two security boundary rule. And what that means is that we always want to ensure and engineer into our systems at least two distinct security boundaries, such that no one single flaw can allow malicious code, hostile code to break out. And in the case for Google Compute Engine, which underpins a lot of our cloud infrastructure, including Kubernetes Engine and many other things, those two boundaries happen to be these two pieces of software here, KVM and VMM, our purpose-built VMM. And I'll talk a little bit about what each of those are and kind of how they compose in this stack and what the security properties of them are, and then how and where we had to apply these mitigations on top of them. All right, so what is KVM? KVM is the hypervisor that's part of the Linux kernel. This is what the majority of our cloud infrastructure is based on. And it's open source. Google's invested quite a lot into finding and fixing vulnerabilities in KVM and getting those vulnerabilities patched and pushed upstream. We've also invested a significant amount in reducing the attack surface in KVM, reducing complexity, taking devices out of KVM into the host kernel and pushing them up into user space, where they can be further and better sandboxed in that user space VMM. Right? And so the investment here is to ensure this is a primary security boundary, is as hardened and as minimized as possible. But yet still, something like Spectre means that if there is a vulnerable branch target inside of KVM, a virtual machine could potentially read the memory of the entire host machine. It's a significant concern. Okay. And then up in this user space portion is a purpose-built virtual machine manager that Google built. Okay. And why we went with this approach? Well, we wanted something that was really small in attack surface. We wanted something that was built for security from the ground up, applying all of Google's best security practices and tooling to it. And we also wanted to further be able to sandbox this thing itself, right? To make it an even stronger security boundary. There's one of these user space VMMs for every virtual machine that runs on the system, and each one of these is itself isolated and sandboxed. So the idea is, if you think about this multiple boundary type philosophy, if a workload were to break out and compromise its VMM, that VMM itself is further sandboxed and unprivileged and wouldn't actually give them any additional information without some subsequent second vulnerability in the host itself. Okay. But again, something like, say, Meltdown, well, now would mean if somebody were in the VMM, they could read through the Meltdown vulnerability all of the memory of the host, including all the memory of the other virtual machines in the platform. That simply won't do. So we have to apply and think about a series of mitigations here. Okay. So what were those mitigations? The first one was something that we developed, an engineer on the kernel team at Google, Paul Turner, developed called retPoline. I'll talk about that in detail in a minute. But really, the point I want to emphasize here is it was our familiarity with KVM, the fact that we spent so much time doing vulnerability discovery and fixing and attack surface reduction in KVM that allowed us to know exactly the right places in KVM that we needed to patch and apply this retPoline fix to address and mitigate that Spectre variant 2 that applied to the hypervisor. Likewise, mentioned Meltdown. There's a mitigation there. We also had to apply KPTI. It's kernel page table isolation. I'll talk about that in detail here in the next couple slides. But this required not only for us to update the operating system on our host machines, Linux, but also to coordinate across the industry, working with all operating system vendors to get all OS images patched with this type of technology. And then also there was that variant 1, that bounds check overflow. That meant going and essentially working with the compiler team, working with the operating system team, and looking for those vulnerable gadgets to exercise them and remove them. Okay. So to go a little bit deeper here, even more into retPoline, what retPoline was a realization that, look, this speculative engine that's racing ahead and trying to figure out where things are going to go, and potentially then it could start leaking bits based on branch movement of the speculative engine, we actually could trick that. We actually could trap it into essentially an infinite loop that would grab that speculative engine and basically make it realize, well, there's actually really no interesting branch here at all for it to speculate past, and essentially trap it in. And then when it came time to actually really execute past this branch, we could self-modify a little bit of that code and then open up that, and the real execution, when the real instructions were issued, would actually then go past and go beyond it. So it's this captive behavior that actually is what makes this retPoline invention work. Okay. The other nice property about this is it has very little impact on performance, right? We don't want to just turn off speculation across the board because the performance of most modern CPUs would be impacted dramatically. But what we can do is we can very selectively, surgically insert this into those vulnerable branch points and ensure that the speculative engine won't leak information across those. Shifting back over to this other thing, kernel page table isolation, KPTI. This was some technology that was derived from Kaiser research into, essentially you can think of this as what we've been doing for many years is having a single page table for both user space and kernel addresses. Okay? And what that meant is that if you were in user space, normally if you tried to address the kernel memory, high memory above a certain address, there'd be a page fault. Right? Can't do that. Right? The page table entry says, well, this part of the memory address is for user space, this part is for privilege for supervisor, for the kernel. And the problem is that Meltdown just blows right past that. So what we had to do is go ahead and take the hit to say, okay, well, we've been doing this single page table strategy in operating systems for decades for performance reasons, right? Because whenever you switch page tables, you have to flush all the past translations, start over from scratch. And if you're switching back and forth between user and kernel, that's really inefficient, really slows things down. But conveniently, a few years back, modern CPUs started to introduce this idea of a tag TLB. This is a way to divide up that translation buffer so that you can have essentially translations remain in the buffer between different page tables. Well, now, rather than switching from one page table to another page table and having to flush everything and rebuild all those translations again, really slow process, I actually get to leave them in the TLB. And then when I switch address space to address space, I just switch back and forth between those translations. They remain resident, and I don't have to flush them out. So now with this in place, then, I can split up my page tables, and that means now that user mode can't actually melt down through to any other addresses other than its own because there are no kernel translations available to it. It actually has to take the full transition, which stops the meltdown problem. And again, thanks to this tag TLB, PCID is one particular implementation, the processor context ID feature, really speeds things up. Again, this also ended up having minimal performance impact. So I just talked about the things that we did to patch on the host, right? This platform, this infrastructure. It was also important to make sure that the operating systems that run on top of this infrastructure, say inside these VMs, themselves were also patched. And so this was very much a kind of industry, everyone having to work together to have this ready to go in time for the announcement, right, when it became public. And this was a collaboration that's driven by very experienced vulnerability responders at Google and connections and through with the rest of the industry. So now I've talked about this, then how do we actually then get this out in production? And in particular, get this out in production before the world knew about it without actually sort of tipping off what was going on. Okay, so this is another technology that we have at Google, underlying the Google Compute Engine, called Live Migration. Live Migration, technology in many virtualization platforms, including KVM and our purpose-built VMM, that allow you to move the entire contents of one virtual machine from one physical host over to another. And importantly, do so without actually disrupting the workload. You don't have to restart the operating system. You don't have to restart the workload. You don't even have to reconnect existing sessions. Okay. Quick overview of kind of how this works. You take a virtual machine, you start to copy all of its memory over to another physical host machine, and essentially you're trying to reconstitute that VM over there. So eventually, over time, you get all of the memory copied over, but there's always constant memory churn because the VMs are left running the entire time you're doing this. But eventually in time, you get most of the memory state synced across, and there's a short blackout period where you have to pause this virtual machine, get the last little bit of memory and CPU state and device state moved over to the other reconstitution version of that virtual machine, restart it over there, re-steer all the network connections, and then let it go again. And we're able to do this in just an order of milliseconds operation with very minimal impact or really no noticeable workload impact at all. And in fact, this is a system that we apply and we do regularly at Google to patch the host operating system, to patch the VMM, to apply microcode updates to the host machine. And so as a process of doing this, we're able to essentially move all the workloads off of a physical machine, patch that host machine for whatever needs to be done for servicing or for security reasons, restart that, move VMs back, and essentially just shuffle through an entire zone within GCE and roll out these patches, these updates. Again, without the workloads being impacted, or customers really even being aware that this is happening. Amazingly, then, with this in place is we were able to apply these patches in the host for Spectre and Meltdown over the course of the month of December without anyone noticing. Right? And not just for GCE, we actually did this across the entire Google fleet to make sure things like Gmail and G Suite and Search and Docs and everything else also had all these patches in place. And it's kind of interesting to think about, like a system that starts and runs 4 billion containers a week was able to be patched for these issues without anyone noticing or realizing it was happening over the course of a month. I've talked about the technology that made this possible, but also it took people, right? It took people and process as well. The way that we often operate with Google is sort of as a volunteer firefighter type model, right? Where there's a major issue, okay, we have to do something about this. Let's pull together people that are experts in their field, whether it be compilers or virtualization or operating systems or CPU design, as well as cross-discipline, right? It requires communication and coordination and response and marketing, PR. Everyone has to come together to make this actually work. And this is not the only time we do this. We do this quite regularly, right? I'm talking about one particular incident here. I'll talk about another in just a minute. But essentially, I would say that it's this relationship, it's these connections that we have that really make this process work. And the end result is, as I mentioned, we were able to patch Google for Spectre and Meltdown without anyone being affected and without anyone realizing it was happening. And this is a proven process, one that essentially we've established now can work against this new class of vulnerability, like Spectre Meltdown type things, and it's one that we've proven in production. If you want to read more information about the actual details, go far more detail. We could spend an hour talking about each one of these different variants alone. Got the links here to the more information about that. Definitely recommend reading that. And now I'm going to transition to talk about another interesting incident, right, that happened. This was a 2014 App Engine attempted breakout. I'm going to talk a little bit about kind of, again, somehow this technology applied and helped manage and mitigate this. Also a little bit kind of what it looked like from the inside, and then how all of our process and people, everything come together. So quick background, some context here. In 2014, a security researcher, Adam Godowak, expert in finding issues with the Java virtual machine, right? Finding ways for Java code to break out of its sandbox, started to actively do research on Google App Engine. All right, so, what is App Engine? App Engine is a managed application platform that allows users to deploy code to Google, whether it's PHP, Python, Go, Java. We take and host that, and you don't have to think about the actual infrastructure underneath that. Well, that Java part is interesting to a Java security researcher, and he wanted to understand just how strong that Java boundary was. And in fact, well, we sandbox, as I mentioned before, right, to make sure that the attack surface is reduced, to make sure the layer underneath, whatever the thing is that we rely on a sandbox is tightly locked down. But again, I mentioned the two-boundary rule. So whereas the Java VM was a boundary in the system, maybe it wasn't the only boundary. And so kind of walking through the sequence of what happened and what this looked like. The researcher poking around the platform, trying to look at how we were structuring how things were done, where the boundaries were, whether his experience and knowledge in Java would apply here as well. Started to poke. What that looked like from our point of view is on December 5th, we saw a lot of interesting alerts and a lot of things start to light up. Like somebody's actually doing something very active against the platform, something somewhere maybe where they shouldn't necessarily be. We didn't know who it was, or what they were doing, why they were doing this, but we definitely knew something was a serious, major issue. So we froze those instances. We suspended the account to look at this, understanding exactly what was going on. And so what was going on is, yeah, we were depending on the Java virtual machine as a first security boundary in App Engine. Right? We were relying on that to constrain the behavior of the programs that were deployed so they couldn't do things like issue arbitrary system calls or run arbitrary binaries on the host. And we'd gone through and done a lot of meticulous work in the Java VM itself to sort of reduce that attack surface and apply these restrictions. But it wasn't something that the Java VM was actually really originally ever designed for. And so it was a process that we had to sort of apply and add on to these things. And the security researcher was finding weaknesses and flaws in that boundary. Okay. What it highlighted to us is the challenge, the issues around relying on the Java VM as a security boundary, and helped to motivate the development of stronger sandboxing technology at Google. But the other thing that was happening here, and this was the interesting part, is the next day, so December 6th, the security researcher went on to the full disclosure security mailing list and said, hey everybody, I've been doing research on Google App Engine. I think I may have poked a little bit too far and gotten a little too aggressive because I got shut down. I got detected and shut down right away. And that was the moment, and that was actually the point at which we realized, okay, well actually now we know who was doing this and what their motivation was. Maybe they should come and talk to us. Maybe we should work together on dealing and fixing these vulnerabilities. Because what they actually had done is they'd broken out of one sandbox, but they'd landed right back into another sandbox. And a sandbox that wasn't Java, right? Two distinct different types of sandboxes, different technologies, different skill sets, different vulnerabilities required to get through. But it was a place where we could monitor and see very anomalous behavior, respond, and shut that down. And that moves into new technology and new sandboxing technology that we developed, something called gvisor. Gvisor is sandbox technology that was derived from research into operating system level virtualization. Right? We think of virtualization, we usually think either really low level, like machine VMs, right? Emulating CPU and device behavior, or we think about these language level VMs like Java. The idea with gvisor is actually there's a maybe even more efficient way to sandbox and isolate applications by emulating system call behavior. And so essentially we're emulating an operating system, not a machine, not a language, but an OS at the system call layer. And in fact, with the development of this now, we're able to run the majority of untrusted code at Google on top of gvisor. And it's significantly more efficient than trying to fall back to running everything into large virtual machines. We open sourced this earlier this year. If you're interested to learn more about gvisor, we have an entire talk on that coming on Thursday. I definitely recommend going to take a look at that. Or go up onto GitHub and you can take a look at the source code for it. So the end result is, with this series of technology and our incident response process and the multi-layers of sandboxing, we're able to detect and constrain and confine an attempted breakout of App Engine by a noted security expert. The other thing about this is in doing so in such a way that they were still confined. Didn't impact anybody, didn't impact other customers or other user data. The other thing that this leads into is the vulnerability rewards program at Google and why this interaction and outreach with security researchers is so important. We ended up developing this relationship with this security researcher and to find and fix more issues within App Engine so that customers and users could be safe. To talk a little bit more about the vulnerability rewards program, I'm going to hand it back over to Andy.
Thanks, Brandon. So as Brandon alluded to, the vulnerability reward program was something that once we had the connection with the security researcher, we were able to pull them into that and engage with them in that. And kind of to step back a bit, the purpose of the vulnerability rewards program at Google is really around turning what is traditionally an adversarial relationship between security researchers and software developers and software providers into something that's collaborative and creates value and wins for the security researchers themselves, for the software provider, and really most importantly for the end customer. As security researchers get rewarded, both in terms of recognition and actual financial compensation for their energy, for their ingenuity, for their interest in digging into things deeply, and us as software providers get the benefit of that additional set of eyes working actively to improve and find flaws in the software. And as I said again, end customers benefit because the quality of software goes up. The Vulnerability Rewards program at Google was started in 2010, over 8 years ago. And to date, we've paid out almost $12 million in rewards to that. So in addition to the recognition, and some folks do this for recognition, some folks do this, security researchers do this to just improve underlying software, and some do it for the benefits of the financial reward. But as we look at it, it really promotes things like ethical hacking. And over the time, as the program has evolved, we've expanded the program to cover not just Google and cloud, but Android and other services at Google each have their own parts of the vulnerability rewards program. Also, as times evolve, we've continued to increase also the financial rewards tied to particular vulnerabilities that are found. Just recently, we elevated the reward found for sandbox escapes from $20,000 to $31,337. And if you want to know where that number comes from, you can talk to me after the call, after this session. So once we're able to bring this together, the security researcher, and therefore able to really understand what was going on and resolve the incident, we were able to then go mitigate the issues on App Engine and then proceed forward and start looking for the next incident. To talk a little bit about that, we've talked about, and Brandon's covered, a lot of the technologies, process, and people around Spectre and Meltdown. And in both Spectre and Meltdown and the 2014 App Engine Breakout, the overall process of how we do detection and response at Google was the same. So as an overview, we have experts in SOCs around the world that follow the clock on a 24/7 basis. From an overall standpoint, when we think about the problem of detection and response, we actually break it into two parts. First is an underlying pre-fail component. So how do we proactively understand how to assess our own attack surface, our own potential risks and vulnerabilities, what are the things that are being done to specify using policy, the things and behavior that should be, how do we actually build protections, like we talked about on the two-boundary rule, the sandboxing, that inherently build a structure that's difficult for the aggressors to get through. And in a lot of ways, the two-boundary rule, the defense in depth, is trying to flip the story, really, from a case where traditionally attackers have the benefit, right? They're hiding within a number of signals, and as a defender, there's a needle in a haystack problem trying to find them in the midst of everything. And flipping this in a multi-boundary situation to where the attacker has to be really careful because they have multiple layers they actually have to get through and try to escape detection. And that's trying to balance out that attacker-defender relationship. In addition to the pre-fail pieces and the protections, we then obviously have monitoring and logging, which allow us to both understand if the pre-fail configurations and specifications we've said drift, as well as to handle the post-fail case, to actually detect when there's an actual incident. And as Brandon outlined before, in the two examples, go through the rest of the process to bring in that volunteer firefighter approach, to bring in experts around the different aspects of Google to address these things. And when we think about the post-fail detection response process, it is also multi-staged, right? There's the process of detection itself and the signals database that we built out to be able to do this, the alerting, the actual response itself, which can be either straightforward or significantly complex when something's at the scale of Spectre and Meltdown. And then communications internally, communications to the product teams, communications to customers, communications to other entities that are involved in the situation, and ultimately for us, the learning feedback. So both at a human level, a process level, and also machine learning technology level, so that we're better, and so that each step, each next thing, we can further reduce the time to detection and further reduce the time to mitigation. So our security teams had the benefit of very integrated forensic set of tools, whether it's to do live memory forensics or disk forensics, timeline analysis, and tie all these different threads together, and also the automation to do that at scale. We've actually open sourced a number of these tools so that our customers and the community in general can benefit. Folks of you who are in the industry are probably familiar with GER, Turbinia, Recall. These are a number of the tools we use every day, TimeSketch, which are all now available on Git as open source tooling that you can use yourself to also build out your forensics toolkit. And one of the other things is, as probably you might anticipate, Google is one of the most targeted sites across the world. So from that benefit, our security teams have to be ever vigilant. And there's the classic problem of garrison fatigue, right? If you're vigilant on standing on guard for an extended period of time and don't get many actual incidents or pieces the systems have protected you against, how do you still retain that vigilance? So we have an active culture within Google of red teaming, of Google on Googling. And that's a key thing. And again, uses the same philosophy we use in our incident response. It's a volunteer firefighter approach. So we get some of the key experts to go hack sometimes and attack their own code, other folks' code within the products, and that kind of both energy and spirit, as well as that really putting the highest level expertise and visibility on particular types of red teams enables us ourselves to quickly find vulnerabilities and flaws in the system. Though we don't play out the VRP for our own internal employees, to much of their unhappiness. So if you look at the kind of overall threat detection pipeline, once we see something, you see that cycle of looking at logs, observing, then actually orienting in terms of figuring out from a security analytics what's going on, actually making decisions about, like, from the underlying pieces what to do, and ultimately taking those remediations. The top part of that is technology and process centric. So we have the advantage of large-scale data ingestion pipelines, threat detection pipelines. Some of those things you guys have seen as a part of Google Cloud Platform. BigQuery is something that we use internally as well to do a lot of our signals and logs processing. And then from an ingestion standpoint, the ability to really take in and handle all that scale data. The last point, and I want to reemphasize what Brandon talked about as well, is you can have the greatest technology, you can have the greatest process. You also need really, really strong people in this space. We're very fortunate to have the advantage of a lot of experienced folks in this space. And as I think you've heard throughout this talk, given all the different aspects of some of these vulnerabilities, especially something like Spectre and Meltdown, the multidisciplinary nature of the skill set needed, readily available in-house at Google to address things, whether it's processor architecture, compilers, OS, virtualization, underlying hardware. All those pieces can come together. And then an equally important thing is, as one of the largest targets, also one of the biggest contributors to security for the community, we have tier one relationships with other similarly skilled organizations and entities, and that allows us to be in the loop for a lot of these discussions. So as I mentioned previously, the SOC that we use is 24/7 around the world, and the underlying teams really include not only the subject matter experts, but the mix of security engineers, analysts, and also forensics experts. And so the bottom half of this loop then is really around the human aspect of it. Top half being technology and process. We also need the humans to actually make the decisions, the right decisions, as Brandon talked about, where to put mitigations like Reptiline, and where to actually do those with lowest impact on overall performance. So to summarize, given something at the scale of Spectre and Meltdown, which again were fundamental flaws in most modern microprocessors that impacted the entire industry, for someone who is a Google customer, it was a non-event. Customers didn't have to do anything, customers were not impacted, and that really is kind of the nature of some of the security and design infrastructure that we put in place, and the ongoing aspiration of how the team works. And then to summarize then, as we've talked about through this, in order to achieve that type of result, we really do need proven technology, process, and people. And it starts with the core philosophy around Google that Brandon and I both talked about, this defense in depth, no single point of failure, that at least two boundary rule built across all the services and all the components within Google. Where we are very fortunate to have that ability to have an end-to-end ownership of the hardware, the software, many of things purpose-built. So then also that deep understanding of the underlying technology, so to know where to put mitigations and fixes, where they have the highest impact on the actual security instance and the lowest impact on end customer performance. As I think Diane highlighted in the keynote, the consistency of our infrastructure, homogeneity, the kind of ability for really us to manage our infrastructure in the commonly used phrase as cattle, not pets, so that you can have automation, scalability, and you can do patching, detection, all of these at scale. And then really the proven response and remediation process, and at the end of the day, that experienced multidisciplinary team. So we designed the solutions that addressed the flaws found in Spectre and Meltdown so that they could be mitigated across all of Google and for all of Google's customers. And we applied patches to the full fleet of Google, including GCE, in one single month before these attacks were public. with, again, no effort from customers and no noticeable impact on them. So with that, I'd like to conclude the talk and invite Brandon back up so we can take some questions. I think there's a floor mic at the end if you guys have any questions.